Hey there, welcome back. So, what are we going to do today? I found the attachment for the project. Here it is. I'll just go on LibreWolf and okay, the project description. So this is the course. This is the course name for MIT. We can find that on MIT OCW website, and we will also find the attachment over there. So okay, this is the projects, and this is where I found the zip file. So as you can see, this is the zip file. Wait, okay. So this is a zip file, and if we unzip it, this is what we find. Inside that, we can find the code for it, code and other readmes. So let's go. Desktop and MIT. I'll just full screen it. Yeah. Okay. So this is what we find. Let's first read the README. Okay. So welcome to project 3. You will write a customizable memory allocator. Let's take a look around. Remember to also read the project handout for a high level but detailed overview. We did that in the first video. Yeah. C code. The main program able to run your allocator on or more traces is mDriver, memory driver. Yeah. And files you should modify: allocator.c, validator.h. Yeah, these are the file we also discussed in the first video about allocator.c. Allocator.c has multiple different functions. We will take a look at it. Files you should look at. Yeah. So we are not supposed to modify it, I guess. memlib.c, memory functions you should call. This is what this is what it has the functions. So to get the program break values and to increase the heap and other different functions. So mDriver.c, mDriver, which calculates throughput, calculates utilization, calculates the heap checker, which you are strongly recommended to write. Yeah, okay. Calls the heap validator, which you will write. Bad allocator.c, bad allocator. Your heap validator should show an error. Okay. On each trace, you are scored in. Okay, so I think these are like the scoring stuff. So we will not cover that. Although these are really important, even if this is the MIT course stuff, and the people that actually were in this class, they had their I can say points based on these benchmarks, but we'll still be using this so to benchmark our own stuff. So okay, mostly our comparison will be against the traditional allocator versus our custom one. So okay, so this is we also read this inside the project description of what mDiver has different kind of flags. So we'll also take a look at the traces that we will be able to find inside the traces directory. Wait a minute. Yeah, okay. And okay, so this is the traces. Let's take a look. The traces are simple text files encoding text file encoding a series of memory allocation, deallocations, and writes. In particular, they include A, pointer ID size, allocate memory malloc, okay. F, pointer ID, deallocate memory free. R, pointer ID new size, reallocate memory, and yeah, the pointer ID, so reallocate function takes pointer ID and the new size, and W, which is write memory, okay. The traces comes from many different places. Some are generated from real programs, others were generously provided by Snail Speed Limited. Uh, Rumor has it that one was generated straight from Teams project to implementation. Okay. They have the file name trace underscore C class V variant. One variant from each class is in traces directory. More variants from each trace class in the additional traces directory. This allows you to examine multiple variants from each trace class and decide how your allocator can optimize for them. Okay, so we have like classes and variants, and like, okay, more variants from each trace class are in the additional traces directory. Okay. Yeah, we'll take a look at it. Uh, okay, when grading, your allocator will see one trace variant from each trace class. It will be one of the variants given or one freshly generated, because there are different traces classes and slightly different variants within each trace class. It's probably a good idea to be general where appropriate, instead of hard coding checks like if size is equal to 47, do optimization. Okay, so we should not like hard code stuff, because we are seeing like the traces have a particular like a particular kind of like pattern, so we are not supposed to hard code the pattern. That is very like, okay, that is very like what am I supposed to say? Okay, just skip it. Use tuning, as optimizations that work well on some trace classes may not work well for others. Okay, mdriver.py script can be used to benchmark your implementation. For each trace class, it compiles your code with a trace class equal to trace class macro. Okay, the mdriver.py script can be used to benchmark your implementation. For each trace class, it compiles your code with the trace class equal to trace class macro, runs and records the score, then computes the average score across all trace classes. Useful mdriver.py options, mdriver.py-trace file, okay, for that particular trace file, and additional traces. Yeah, sure. The open tuner. Okay, so this is the open tuner that we found, that we read about. I think we should just skip it for now. I don't think there is anything more to read from this. It's just about OpenTuner. Okay, so let's take a look at the code now. So I think I should zoom a bit more. Okay, let's take a look at the code. So this is the code. Right now, I should just do this. Yeah. So additional traces, short traces. We'll take a look at all three of these. We are also supposed to take a look at. So we are supposed to modify allocator.c function, allocator.c program file, and validator.h. Where is validator? Yes, over here. I have to change this, and okay, I think the rest of these are like okay. I think we will also take a look at allocator interface.h. What is allocator.c? I think we'll take a look at like important ones like allocator interface, allocator test, allocator, bad allocator. I think these are like system ones, so we'll skip them. libc allocator, okay, we will take a look at that. mdriver.c, and then my allocator wrappers and validator. Okay, let's start line by line. Okay, not line by line, but let's start from the important one, which is allocator.c. This is the main one that we have to write. Okay, so MIT license, the above copyright notice and this permission shall be included in all copies or substantial portions of the software. Okay, yeah, sure. So let's start. Yeah, I think this should be visible. I can't see. Okay. Let's start. Don't call libc mallocs. Okay, yeah, we are not supposed to call the libc mallocs, which is malloc free realloc. We are supposed to use our own, as you can see, use my malloc. Okay, that's fine, sure. All blocks must have a specified minimum alignment. The alignment requirement from config.h is greater than or equal to 8 bytes. Yeah, as we read previously, the alignment is 8. And define align size, round up to the nearest multiple alignment. Okay, so this macro does what? So it takes size plus alignment minus 1 and not of alignment minus 1. Okay, So it gives us like the what you can say, the multiples of 8. Okay, so let me just ensure this. So okay, I think it's supposed to, like, alignment is like 1 0 0 0 2 to the power 3, and then oh no, it's alignment -1. Sorry, my bad. Alignment -1 is 7, so 0 triple 1, and alignment -1, not of alignment -1 is 8 itself. Yeah, so 1 triple 0, and we have to pass and, so it's 0 again. Oh, it's the, oh, I'm so dumb. You're not supposed to do and operation with this. Okay, so size plus alignment -1. Let's consider size as let's take size as 16. So 16 plus allocator alignment -1, which is 7. So 16 plus 7 gives us 23, and so 23. So 23. How does 20 look like? That's 23. 16, so 1, and then 8. No, we can't take 8. Okay, so I guess 1 0 1 1 1. What is this? 16 16 4 2 1. This is 3, and this is 23. Yeah, 1 0 triple 1 is 23, and 1 0 triple 1 is 23, and so alignment -1 is 7, and not of 7 is 8 itself, which is 1 triple 0, and we have to perform AND operation on them. So we get 1 0 0 0, which is a power of 2, and I think it is a multiple of 8, which is 2 to the power what is this? It's 16 again. Yeah, got it. If you don't believe me, I did do the calculation. Oh, sorry. Where? Okay. Oh, sorry. This is my timetable. I'm supposed to show this. Yeah. So this is the calculation that I was doing. So 23. This is what 23 looks like. This is the AND operation with alignment minus the not of alignment -1, which is 7. So not of alignment -7 is 8, and this is the AND operation, and we get 16, which is a power of 2 and a multiple of 8. That is great. So okay. These checks are invariant, that the size tree header before every block points to either the beginning of the next block or the end of the heap. Okay, these checks are invariant, that the size tree header before every block points to either the beginning of the next block or the end of the heap. Okay, let me just understand that again. My small brain can't understand it. The smallest align size that we hold the size tree value. That is this is fine. The smallest align size. That is fine. Okay. These checks are invariant, that the size tree header before every block points to either the beginning of the next block or the end of the heap. Okay, got it. I did not understand that still, but I'm just going to, okay, I got it. Maybe I'll understand it later on. So here, char p, the low is mem heap low, mem heap high plus 1. We should take a look at these functions. So okay, I do have to learn how to use multiplexer, uh, but okay. For now, I'll just use a new tab. Okay, so I think it's inside memlib.c. Yeah, mem. What was it? Mem heap low. Mem heap low. Yeah. Return void pointer. Mem start brk. Mem start brk. Static mem start brk, and that occurs when we allocate it. Right? It returns. Okay. Mem heap low. Oh, sorry. Mem heap low returns the address of the first heap byte. Okay, that's great. Mem heap high. Sorry, it's supposed to be, yeah, mem brk -1, and mem brk will be, oh, there are very different things over here. So I guess the initialize, yeah, this is where I think it's happening. So yeah, mem brk, mem start brk. So mem start brk, we malloc max of heap. Max of heap is max of heap. I think it's inside. Yeah, I think we won't find it over here. I think it should be inside allocator interfaces. Allocator interfaces. Max. No, it's not over here. Max heap. Let's go. Yeah. It's inside config.h. Okay. Config.h. Sorry. Yeah. So it's 50 MB. Okay. Got it. So we allocate a size of 50 MB, and if there was no error, if there was error, we print whatever the error is, and if there was no error, we set mem max address is equal to mem start brk. That is fine, and mem brk is at mem start brk. Okay, yeah, the program break is at the start of the heap because there are no processes running currently. That's fine. That's okay. Cool. So if we look at how many functions are there? I'll just cover everything from this. This is the memlib.c. We are anyway supposed to do it. Let's just do this one first, and we'll take a look at allocator.c later on because it's going to use the memlib.c itself. I don't think I can pause this video, and if I pause this, I have to like merge them later on, and I don't want to do that. But I'll just take a break. I'll just come. So this is the continuous video. I cannot take breaks in this one to like. So I've selected the what you can say, like the FFmpeg kind of custom option inside OBS. So I cannot pause this. So I'll just move outside of the frame. I'll be back. I'm back. But let me just have a sip of water. I'm back. Sorry. Let's go. So, okay. So minit is if, let me just take a break again. back again. So let's go again. So mem start brk, so points to the first byte of the heap, and mem brk points to the last byte of the heap, and largest legal heap address. Yeah, sure. Sorry. Yeah. So mem initializes the memory system model. So it uses as we looked at the function earlier, we malloc. So this is the config. So mem init will be run first. It will allocate max heap size, which is 50 MB. If there is an error, it will exit directly. If there is no error, then we set memory max address as mem start brk, which we get the pointer. So whenever we use malloc, we get the pointer of the starting of the memory, the initial. You can see the origination. No, the start of the memory, the starting address of the memory. So we set memory max address as starting of the memory plus max heap, which is 50 MB. So yeah, that's cool, understandable. And mem brk, which is supposed to be the points to last byte of a memory, is mem start brk. So we will take a look at how mem brk will be modified. Like, not take a look, but we will see like how it is modified. So this is the program break. We are not supposed. We are not. No, sorry. So, this mem brk value is not going to decrease. So we have to very carefully do the fragmentation handling and the free list, so as to not use a lot of this. So mem set, memory set, mem start brk 0 max heap, 0 out memory to prevent page faults. Okay, so we zero initialize, I guess, every single one of it until okay, let me just take a look at the parameters. Mem set function in C. Clanker detected. I'm not going to read that. Although, yeah, okay. Okay, so what does this do? Fill 8 characters starting from string 13 with the dot. Okay, so fill max heap places starting from mem start brk with 0. Yeah, sure. That's what I thought it's going to do. So mem deinitialize, I guess, yeah, this is the freeing of the main thing. Fine. Mem reset brk resets the simulated brk pointer to make an empty heap. Reset the simulated brk pointer to make an empty heap. Okay. So mem reset brk. Okay. Mem brk is equal to mem start brk. Okay. Wait, I didn't understand what is happening. So mem brk is set to mem start brk, and we do that, right? I guess to reset it, so if 5 processes were allocated, should I draw a diagram? Let me just erase that stuff. I think I shouldn't be explaining this stuff because I am the dumb one who doesn't understand stuff, and you guys must be understanding every single thing, and you might even not be needing my explanation. I can't, as you can see, I cannot see what is happening. Should I increase this? Okay, let's increase this. So it looks kind of better. Okay. I'll just shift over here. So what is happening? So if this is the heap, if we allocate a lot of stuff, our mem brk is over here. Okay, yeah, mem brk is over here. This is the max address, whatever you call. This is the start brk. This is the max address. Sorry, I shouldn't be writing on that side. This is easier. max address. And so if we do reset, then this pointer will be pointing to this. So we don't need to clean all of this. It just it will just reset. Although I think the reset should be zero initializing all of this again, right? That is valid concern. That is a valid concern because you already said like the page fault and all. Okay, sure. Let me take a break. Not break, but I just have to like do some stuff. How big was it? Okay, is this great? I think this is what it was earlier. So this is fine. Just a minute. Back at it again. So 26 minutes in and we haven't done anything, but okay, let's go. So deinitialize, we looked at it, and then mem reset brk, we also looked at it. Mem sbrk, okay, this is the main one that will be increasing the memory. That will be modifying the brk, mem brk value. So mem sbrk, simple model for the sbrk function, extends the heap by increment bytes and returns the start address of the new area. Okay, in this model the heap cannot be shrunk. Sure. Although, should we add that? No. Okay, that is for different. We'll do it later on. Okay, so if mem brk plus increment is greater than max, so we don't want it to exceed the max address, which is we do not want it to exceed 50 MB. So yeah, fair. Mem sbrk field ran out of memory. Sure. And if it's not, then character pointer of the old brk is equal to mem brk. Sure, we store it in. Yeah, should I show it? Yeah, I think it's the Richard Feynman's technique. It's like if you want to better understand what you have learned, is to explain it. So where is my duster? What the? Okay, just a minute. Just a minute. Back at it again. Sorry. Back at it again. And yeah, let's go. Can I hide these controls altogether? Oh, this is what I was supposed to do. Like, okay, I'm a dumb guy. Sure. Oh, does this change? Okay. Oh. Wait. It doesn't modify quality, right? It shouldn't be. Okay. So it's fine. I'll just do this. Push you guys a little back. So, okay. Yeah, we'll make a better heap, you know. So what's happening is, so this is the, let's say, along this line. So this is max address, which is 50 MB. This is the initial mem brk value, or you can also say mem start brk also. This is also the mem start brk value. Okay, and our concern was, yeah, so what happens is that if we allocate a process, let's say this is a P1 process and this is already present over here. I should draw better P. Let's say this is process 1 and this was already there. Okay, now let's say we allocate P2. So what will happen is that if we allocate P2, this pointer, which is membrk, should increase, and this will, let's say membrk will be initially pointing over here, and when we allocate this extra memory, membrk pointer will now point to this stuff, right? membrk will point to this position. But the thing is that when we are allocating when we allocate an extra memory, when we move the program break pointer, we have to return the start of the new allocated memory, which is this. So this was the earlier brk value. So hence we are storing the membrk earlier value into old brk, which is here, and then membrk is getting incremented, and we are returning the old brk value. That is cool. That is not cool. That is what we are supposed to do. I'm like learning all of this stuff, so I'm like appreciating every single thing that I'm learning. But okay, I guess that is a good thing. I shouldn't be like saying anything about it. That's a good thing. Appreciating is a good thing. Okay, I'll reduce this again. Why didn't I do this for like whole screen for show you guys? I'm okay. I'll do it next time. I'll keep it this much. This much looks cool. Let's go. How far are we in? 31 minutes. That's great. So heap low. Okay. So heap low. Heap low gives us the mem start brk value. Okay. Sure. Mem heap high will give mem brk -1. Yeah. Sure. Like the current mem brk value -1. Sure. That is cool. Heap size will give us mem brk minus mem start brk. Mem brk minus. Okay, how much have we used? That is the heap size in bytes. Okay, so how much of the heap have we utilized? And mem page size is get page size function. Get page size function. I haven't. So this I'm using Noob, and we are supposed to like add. Sorry. I'm using Noob, and I use Noob by the way. So in that, people usually set up like GD, which is a go-to description. I haven't set that because it comes along with the LSP. So I don't like I don't like clankers modifying what I'm typing. But okay, I'll do it later on. Yeah, that's a good thing. It's not like a bad thing. Okay, so get page size. So I can't just run GD. Sorry, I can't run GD on this. As you can see, it's not doing anything. So get pages size. I don't think it is inside this file. Yeah, we'll just use our RG get pages size. It's a wait. No. I want like the declare it. Wait, what is get pages size like internal function? What? Yeah. What? Get page size. If we look at what are we including? Oh, okay. So why didn't we see that? Wait, what? I did try that, right? Get pages size. Oh, okay. I should have. I think I mistyped that. Mistyped that. So okay, get page size, get system page size, standard C library. Whatever this is, I cannot pronounce that. Like I just say unist. Okay. I don't know the full form. It's fine if I don't know the full form. You know, I'm learning stuff. What is it called? That provides. No, I want the full form. Put it out. Full form. Yeah. it's fine. Okay, and standard, what is it? Standard, universal standard. Okay, I nearly guessed it. I did not look at that, but I just guessed it. Universal standard header, whatever. Just okay. So universal standard header, get page size void. This type of what you can say, coding design pattern, that's good. So get page size function returns the number of bytes in a page. Page granularity is the granularity of many of the memory management calls. The page size is the system page size and may not be same as the underlying hardware page size. Okay. Page size 1, SBRK2. Okay. Page size, get page size. Yeah, that's fine. Cute. Let's go. Let's go, boy. And now we have completed every single function from memlib.c. So let's go back. So mem heap low. So now I can I can understand every single stuff. So yeah. So here we'll run. Here we'll get the low, which is the bottom value, which is the start BRK value. Heap high will give us will it give us the utilized stuff, or like the high, like the utilized stuff. It will only give us the address of like membrk. Yeah, got it. So size is 0 and p is p which is the pointer, initial pointer, and it is currently at low, that is fair. And while low is less than or equal to p, well, low is less than or equal to p, yeah, sure, we are not supposed to like free up more than we are supposed to. And p is less than high, yeah, sure. Less than high gives us the what. So this will be run by traces, and then we are supposed to only allocate in inside what we are supposed to. Like we are not given like free range over the memory address like 50 MB. We are just given free range on the whatever the traces have allocated to us. So okay, size is equal to align size t p pointer plus size t size. Okay, so size is equal to align. So this, so we'll get a pointer. So let's say we are at 0. What if we are at 0? No, I don't have to do the calculation. We'll just be at the multiples of 8. Okay, size t underscore size. What does that mean? Size t size. What is size t size? Let's take a look. Size t size. Align size of size t. Oh, it was above. It was over here. This is what it was. Sorry, I forgot. How did I forgot that? How did I forget this? Okay, yeah, sure. Okay, I'm a dumb guy. We're just +1. Okay, so if p is not equal to high, then bad errors did not end at heap high. Okay, if p is not equal to high, what? If my pointer is not equal to the high value, and a high value is supposed to be whatever the allocation has been done, and p is the pointer. That's correct. P is pointing to the program break, and high is also initially will be pointing to the program break. That is fine, and we return 0. Int my init. So okay, so here I think this is the basic one. So this is the check stuff. But yeah, okay, so from over here, from over here, we are supposed to write the functions and how big is it? 71 and we are at 145. That okay, that's a small thing. It will be growing rapidly though. Okay, so init initializes the malloc package called once before any other calls are made. Since this is a very simple implementation, we just return success. Okay, so we don't have to modify anything over here. Sure. Okay, where's the config happening though? Okay, I will take a look at it afterwards. So my malloc allocates a block of incrementing the brk pointer. Allocate a block by incrementing the brk pointer. Okay, wait. This is the int check. This is the my reader. This is the my free, and this is my init. This is void malloc. Okay. I thought I missed something. Okay, malloc allocate a block by incrementing the brk pointer. Let me just take a look at it. Okay, it's recording. Okay, malloc allocate a block of incrementing the brk pointer, and allocate a block by incrementing the brk pointer. Always allocate a block whose size is a multiple of the alignment. Yeah, sure. Void malloc size t size. We allocate a little bit of extra memory so that we can store the size of the blocks we have allocated. Yeah, sure. As we have, that's what must be happening yesterday when we allocated like 1000 units of 1024 bytes, and it took extra memory. Just I think it's because of the size of each time we asked brk to increase the like whenever we wanted like new allocation. And the brk pointer will be moving. We will also be storing the size pointer to the like the size, not size pointer. We'll also be storing the size value for the newly allocated memory. Okay. Okay, we allocated a little bit of extra memory so that we can store the size of the blocks we have allocated. Take a look at realloc to see one example of a place where this can come in handy. Okay. We'll definitely take a look. Int align size is equal to align size plus size t size. Yeah, sure. Whatever the align size is. Yeah, great. Expands the heap by the given size of bytes and returns a pointer to the newly allocated area. Yeah, mem sbrk. Yeah, sure. This is a slow call. You will still want to make sure you don't wind up calling it on every malloc. This is a slow call. Yeah, sbrk is slow. Don't call sbrk every single time. Instead, you free up the memory that you have already used and better utilize what we already have instead of calling again and again sbrk. So p is equal to void pointer -1. Whoops, an error of some sort occurred. We return null to let the client code know that we weren't able to allocate memory. Okay. We store the size of the block we allocated. Wait. I just realized something. Oh, I think I just realized something. Let me just test that just one time. What was I supposed to have? Is there a make file over here? No, I just can't run make edx in assembly. Okay. Okie dokie. Make green. Okie dokie. Make file. Allocator test. Okay, unknown register name edx in assembly. Is it supposed to be edx like for normal 86 processors? Is that what that means? So I should be copying every single one of it. I'll just copy only this much stuff. Unknown register name edx in assembly 27 in assembly. This should work. Bad register name, what does that mean? Move 3 ECX. Okay, the double person sign for register is used when we want the GCC extender inline. Sorry. With input and output clover list. This is because a single person sign is reserved by the inline. Okay. The double person sign for registers is used. Okay. This is single register. Okay. In clock.c they are saying. Over here. Only two places where it's used. And it wasn't. Oh my god. Okay. I think I know what is happening. I got this, bro. I got this. Oh, sorry. To English. Assembly to English. Okay. So this will remove. Oh, I have to like remove a lot of stuff. I'm too tired for that shit. Yeah, close that. Oh, this is by the way a great site. Okay, so I think does Clang understand EDX register? Why does Clang behave weirdly with register variables? And let's see. I think if this is the case, I think we have to. Okay, everything seems okay until I change my program's compiler to Clang. In GCC, it usually prints something similar to this, whatever. Does Clang didn't support the register variable usage? Why didn't it coupling? So I think this is what is happening. I think Clang is not able to identify like the proper register and stuff. Clang does not support explicit register variable. That's what I thought. I am such a like. Sometimes I feel like I'm a really smart guy, and most of the time, I'm just a dumb guy. Okay. Oosh. Okay, so I'm supposed to use GCC. GCC. Okay, I have to finally install GCC for Mac and Bung. Yeah, okay. How to install? I tried that using Blue, but there was some error declared. GCC-V. It's still Clang. Yes, sure. Make sure you have Homebrew installed on your Mac device. Homebrew search GCC, brew install GCC. You can see GCC-V Apple Clang version. I do have that, right? Hosty GCC-V. I do have that. So what's the problem? Okay. Wait. So what is happening inside the make file? I think most of this video is just going to be like me trying to wrestle with the compiler and stuff. Okay. So where does it usually start? So C flags, GNU stood GNU 99, and okay, headers memory.o. This is not that important to us. If debug is present, debug is not present. Shell pin targets. Okay, yeah, this is what I wanted. So targets in where is the targets? Where is the targets? The CC. Yeah, okay. So let's search for CC clang. It's using clang. So what's the problem? What's the problem, bro? Register name EDX and assembly CC. What? Does clang have a problem with that? So should I modify this to that shouldn't be like yeah. GC sorry, yanking paste GC. Oh shit. Make file, yanking paste, boom, 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 boom. No, still the problem. Is it problem with EDX? What's the problem? EDX in assembly, unknown register name, EDX in assembly. I think I should use Safari. I don't know why, but Google has collected like so much data of ours. Like it is just better at search results, you know. Oh no, Clankos. Sorry, I am so sorry. I think for a small bit of for like a fragment of time, like a very small, like for a few milliseconds, I looked at the clanker, but I did not like read any of it. It's fine. I'm trying to port some open source code to a new platform, specifically GSP from this code. Right now I'm trying to compile and he got that same error. I don't have experience with assembly and define not with ARM. Okay, wait. GSP, Rockbox. This is not Roblox, this is Rockbox. I'm trying to get a compile and work on after fixing many of the errors. I'm left with this error. MOV, home username, Rockbox. I think, yeah, ARM. Is there a problem with ARM? Please. That error comes from passing ARM assembly code to an assembler that doesn't understand it. This is usually the result of misconfigured toolchain makefile when cross-compiling, invoking as rather than cross-compiler prefix as. However, from the feedback in the comments, in this particular situation, you actually have the opposite problem. Right toolchain, wrong code. Since the Rockbox UI simulator is not an emulator, it will only run on x86 code, assuming your host is an x86 PC and you explicitly don't want to cross-compile. Thus, this ARM build will never work nor be useful because the inline ARM assembly. Sure. So okay, I cannot run that code. Fine. It is one of the drawbacks of using like the ARM architecture MacBooks. Okay, it is nearly 1 hour, so I can't run this code. But what my main concern was, I'll explain it to you. Okay, my main concern is I think this is already the ready-made project. Like, okay, this is initializing. Like, it will be using the trace files. So what am I supposed to do? I guess I don't see the fragmentation and stuff. So okay, there is no freeing a block does nothing. So we are supposed to write it, right? Wait. Let me just think about it. So my alloc size t will be incrementing the size t, and from the traces I have to just modify this. Okay, so let me read the project description again just one more time. We'll just end it in the 1 hour segment. So okay, so project description, let's go. So this is what we looked at. And okay, before calling the program, the application program that is a trace one that we will use to evaluate your implementation calls myinit. Okay, you may use this function to perform any necessary initialization as allocating the initial heap area. So I guess we haven't done that. myinit. Okay, got it. Yeah, so this code is not entirely complete. So is just like the basic version. So my init should be actually so if we go in memlib.c where the actual stuff, so mem init, so mem init should be called somewhere, but let's just check, is it called? Please don't be called anywhere other than your own file. This is allocator.test and mdriver. Let's go. What is allocator test? Okay, this is just testing. Wait. Int main, mem initialize, mem implementation, and my implementation. Mem implementation points to init. What is init? Wait, what does this do? Come on, boss, help me out. Is there a readme over here? Just clean it. Is there a readme over here? No, there's not. Okay, sure. So my init, since this is a very simple implementation, we just return success. This is a very simple implementation, we just return success. And wait, where is the project description? Yeah. So the return value should be -1 if there was a problem in performing the initialization, and 0 if everything went smoothly, where we haven't done anything. So we are still supposed to. This is not the this is not the complete implementation we are supposed to write over here. So let's cover this stuff quickly. We store the size of the bytes. Okay, we go over here. So memsbrk and pointer. If whoops, an error occurred. Yeah, okay. So if p is below. No, not below, but if it's like pointer which is null and it's negative, then we just return null, and if else okay, so it's a p is equal to size. We store the size of the allocator in the first size t bytes. So size t pointer of a pointer. Very easy to understand for a beginner. Can p, and we just return that. Okay, sure. So freeing a block does nothing. Realloc implemented simply in terms of malloc and free. My realloc, we were also supposed to take a look at this. So let's just take a look at this quickly and we'll end the video. Okay. So my realloc, what's the time? Okay. Void new pointer. Okay, void new pointer, copy size. New pointer is equal to myalloc size. So we, for reallocation, we call the new size, and then we whatever. So this parameter is the size, is the new size that we want, and then pointer is like is the beginning of what? Shit, I forgot. How did I forget that? Void pointer, this calls a return pointer to other discipline. Pointer is not the size. Calls pointer to an region similar to how malloc works. Okay. But malloc, what is the pointer? Okay. So if we already have a pointer that we got from myalloc, we'll pass it to myrealloc and we'll tell it to increase the region. Yeah, it's quite easy. Okay, so new pointer, mymalloc size, and yeah, sure, mymalloc will get a new pointer at that thing. If null is equal to new pointer, return null. So there was an error. If there was not, get the size of the old block of memory. So you get the size of the old block of memory. Take a peek at the myalloc where we stashed this in the size bytes directly before the address we return. Now we can back up that many bytes and read the size. Okay, so copy size is equal to unsigned integer 8 pointer minus size to size, and it is a pointer to the size pointer. Okay, got it. It's the value, copy size. Where is it? Yeah, so this is the value of the pointer. Yeah, this is the. Okay, should I explain this? even I don't completely understand. I'm just guessing. So pointer is unsigned integer 8 pointer. We get a value minus size t size, and then again we get a value. I am so confused. I do have to, like, I'm not that good at pointers, so I will read that. If the new block is smaller than the old one, we have to stop copying. Okay, if the new block is smaller than the old one, we have to stop copying. Yeah, we have to just resize it, and copy size is equal to size. Yeah, sure. If size is less than copy size, then copy size is equal to size. Yeah. This is a standard library called that performs a simple memory copy. Mem copy, new pointer to pointer, and copy size. Yeah, sure. And if it's smaller, we'll just truncate whatever the remaining stuff was, and release the old block by free pointer. Yeah, sure. And I think I had this doubt yesterday too. What is the pointer? Okay, I guess it's fine. It's fine. It's fine. So okay, return new pointer, and that is done. This is it. Uh, okay, so I guess this is it. We have to work on how to free up the memory. We have to work on the fragmentation, so we don't have to call malloc again. SBRK again and again. So we have to write a good fragmentation thing, like best fit, worst fit. We have to coalesce memory. We have to make a free list. These all stuff, and we'll be starting from tomorrow. So tomorrow is Monday. So usually the stream is going not stream. So usually I'll be uploading videos. I'll be recording videos on Friday, Saturday. Not Friday. Sorry, on Saturday, Sunday, and Monday Eastern Indian Standard Time. I'm not sure how Standard Time works. I haven't like looked at it, but I'll be recording these videos. I'm a complete noob, guys. Okay, I don't know most of this stuff. I'm just learning. I'll be learning about pointers off camera. Okay, off camera I'll be using like ChatGPT, Haxor mode. No, I'll read the documentation and stuff. Okay, I won't be using ChatGPT at all. No clankers in my laptop. Okay, so this is it. I'll close every file. Oh, sorry. Yeah. I'll close this, whatever this was. Close this. Yeah, okay. I'll close this too. So, okay. This is it. And okay, I guess we are ending the video. 1 hour 3 minutes 32 seconds. This is a lot smaller because there was not a lot of stuff that we did yesterday. Like the 2 streams before, we learned a lot of stuff, like a lot of stuff. Like, okay, so I guess thank you. I'm Aditya Pacharne. I'm an engineer for fun. Bye.